Good evening and welcome. I'm happy to see you this evening. I was not expecting so many. Let me remind you before I start, I remind you of course, next week we don't have a lecture, but we have one in 2 weeks' time. I'm not sure if this building will be open, but I will open it and I will check on the day and send you a message. But we keep the same time, same place. And the last lecture is on January 14. So we have 2 more time. And please submit all your reports before January 14 included. And there is an announcement about some activities organized by NUMI about this Connect with Recruiters. So if you're interested, it's probably a good opportunity to meet some people. So have a look at this. So let me start with what we have done last week. I explained I gave you a theorem about bifurcation theory, but for one parameter. So we have a function which depends on one parameter. I call this parameter R, and it's one-dimensional, so the variable x is also one-dimensional. So together, it's a two-dimensional system. And so we are saying that this parameter R0 at this point x0, if they satisfy that the function which depends on this parameter at x0 is a fixed point, and if the derivative of the function with respect to the variable x, again at this point, is not 1, then by an implicit function theorem, we have seen that there is no bifurcation around this point. So if we want to have a bifurcation, it means we need to have this derivative equal to 1. Bifurcation near a fixed point. So if this condition is satisfied, and if this is 1, then we may have a bifurcation. Then I explain what is a period doubling bifurcation. It's precisely when there is something like this which happens, where you have, so the parameter is on the x-axis. This is a parameter. We look at fixed point, and you have only one fixed point in this region, which is attractive, and suddenly you have a period 2, so it means these points are not fixed, but when you are here and you apply f, you switch to this one, and when you apply f again, you are here. So it's a period 2 orbit, and it turns out that between them there are still fixed points, but they are no more attractive. So it means except if you exactly find this point, otherwise you will not see this because you have no way to be attracted by this fixed point. So this is a period doubling bifurcation. Then I mentioned this Sharkovsky ordering. It's a new ordering of the set of natural numbers, and it implies there is a theorem which tells you if you have a n periodic orbit, then you have additional ones with precisely following this ordering. So you can look at the notes. Then I recall what is topologically transitive or topological transitivity. It's defined in terms of 2 sets, and you let them evolve. And it's topologically transitive if there is an n such that at a certain point they intersect. I explain what is the notion of sensitivity to initial conditions. So there is a precise definition, but essentially it means no matter how close you take 2 initial conditions under the evolution, I always represent continuous evolution. It's simpler, but in fact, I should do it discrete because it's a discrete time system. But it's probably more difficult to visualize, so I do it with continuous evolution. But it's sensitive to initial conditions. It's no matter how close you take them, after a certain point, they are going to be far away from each other. It doesn't mean they are going to be as far as you want, because if everything is in a box, they cannot escape and have a large distance, but there is a precise notion for this. And we define a chaotic iterated map as an iterated map which has these 2 conditions. It's topologically transitive, and it has a dense periodic point. So the set of all periodic points are dense, which is probably not so intuitive, even though I gave an exercise which show you that this can happen. But it turns out that these two conditions imply the third one, which is the sensitivity to initial condition. This one might seem more natural or more intuitive, but as I gave an example, there are functions which very simple function which satisfies this, and you wouldn't say that it's chaotic. So the chaotic systems are defined by sensitivity, topological transitivity, and these dense periodic points. And in fact, if you continue this picture for the logistic map, you will see regions where you have plenty of dots. They are precisely chaotic, but inside this region, you still have many periodic points, even though you don't see them, because you would see them if you can exactly get on the top of one. And in order to, we want to analyze F4. So this logistic map was depending on a parameter, and the last parameter is 4. And I want to show that this F4 is precisely chaotic in the sense I have given. But in order to show this, we first studied this tent map. I gave the definition. It's a function from 0, 1 to R. It's also depend on a parameter. And if you take the parameter 2, it's between 0, 1 to 0, 1. So it leaves this interval invariant. But we have shown that it is indeed chaotic. So we have proof for this T2 that it's topologically transitive. We were able to show this property. And we have shown that it contains periodic points which are dense. So for T2, we were really able to check these two conditions, which means it's a chaotic iterated map. And it also implied that we have this sensitivity to initial conditions. And now I want to take the information from this and get it to F4. So there is one way to do it, and I will now introduce it. If you have any question, of course, you can interrupt me. And today we're going to finish this chapter. So again, my aim is to go from T2 to F4. T2 is for the tent map. We were able to show that it's chaotic. I want to go to F4. But there is a notion which I need to introduce. It's a notion of topological equivalence. You will see that it's very natural. So we consider two metric space, but you can think of, you remember, Rn or a subset of Rn is a metric space with a Euclidean, yes? Transitive? Okay, sorry, it's not well written. Transitive. There is a bijection between this word and this word. Okay, so I consider two metric spaces, but you can think about, as a concrete example, two subsets of Rn with a Euclidean metric. So two metric spaces. I still want to keep this abstract notion of metric spaces for the next two lectures. And I consider F1, which goes from M1 to M1. So for example, it's going to be T2. And I want to consider F2, which goes from M2 to M2. They are continuous. So I consider two applications, one from this set to itself, one from this set to itself. They are continuous. The continuity is well defined, either on Rn or on metric spaces. Then the corresponding iterated map. So because we have a function from a set to itself, we can just iterate. So they define an iterated map, each of them. So the corresponding iterated maps are topologically transitive. It's a complicated word, but we will see that it's very natural. Oh, sorry. Now I have to be very careful with the way I write transitive. Oh, no. What is the question?
You're defining topological equivalent.
Thank you. Now he disturbed me. Thank you. Now I'm guilty. Equivalent. Thank you. So they are topologically equivalent. This is what I want to define. If there exists a third function phi from M1 to M2, which is bijective, so you can go back. And bicontinuous. Remember, I already mentioned it once. Bicontinuous means it's continuous, but it's inverse, because it's bijective, we can define its inverse. Its inverse is also continuous. So it's continuous in both directions. Such that, and now I'm going to write an equality, F2 composed with phi is phi composed with F1. And I'm going to make a small diagram for this, because this is something which appears at many places. It's called a commutative diagram. Look at this. I can represent it like this. We have M1. We can apply F1. Then we have M2. M2. So the map going from M1 to M2 is phi. And we have F2 from M2 to M2. And this equality means you can either go through this path, so first apply F1 and then phi, or first phi and then F2, it's the same, right? You can also write it, because it's invertible, please observe that it's the same as writing F2 is equal to, so I can take phi F1 phi minus 1. This is a notion of topologically equivalent. So it's quite natural. These two things are very similar because you can just deform. You think about this as a deformation. You deform the space a little bit, and then you have the same thing. So this is a notion of topologically transitive. I already mentioned something of this type when I introduced the notion of bifurcation.
Arrows for phi are double-ended. Like in your diagram, the arrow for phi has on the
Okay,
yeah, I guess it means that you can go in both ways.
Okay, I copied it from somewhere, some place, and I probably didn't pay attention to this. But okay, maybe I will correct. So this is a natural notion when you have two functions and you want to, from one space to itself, from a second space to itself, and you want to say that they are not so different. So in our case, it's an exercise. I want to show that precisely T4, the 10th map T2, the 10th map, and this logistic equation or logistic map F4 are topologically equivalent. So what you need to do, but I help you, you need to find the phi. You need to find the phi, which precisely, first, let's remember T2 is from 0, 1 to 0, 1, and F4 is also from 0, 1 to 0, 1. So it means M1 and M2 for this application, they are both 0, 1 with a Euclidean metric. So it's easy, but you need to define phi, and it turns out that phi, I can give it to you. It's just a sine function. So sine phi of x is precisely sine of pi x over 2 squared. So what you have to do if you do this exercise, check that this is indeed bijective and bicontinuous. So phi is from 0, 1 2, 0, 1, both bijective and bicontinuous. And you have to check that it respects this equality. Now I don't remember which one is F2, which one is F4 and which one is T2, but you can easily see. Is there a mistake? No, there is no ambiguity when I write this. It's sine of this variable and you take everything square. If you don't like it, I can write it like that. No, this is not ambiguous, please. Okay, so this is an exercise which is not difficult, showing that it's bijective and bicontinuous because we know the inverse. It's not so difficult. And checking that this condition is satisfied, you just write the definition of both. And what it implies, what is the conclusion? F4 is chaotic iterated. Why? Why? If you think carefully, remember we had two conditions for chaotic iterated map. One was topologically transitive, and precisely if you check what means topologically transitive, it is preserved by this map. And the second condition is the existence of dense orbit, but again, the geometry is not very different through phi, so the presence of dense periodic points is preserved. All the information which are topologic, probably not all of you know what is topology, but topology is a mathematical theory of when you can deform object precisely by keeping everything continuous. So for topology, the keyword is continuous. You can just deform a little bit. This is a topology. And precisely the notion of topologically transitive and existence of dense periodic orbit. If you deform a little bit, it stays the same. You keep the same properties. That's why if T2 is chaotic, then F4, because they are topologically equivalent, F4 is also chaotic. This is the way we prove that F4. So you can see on the picture for the logistic map, F4 is the last one. It's a proof that it is chaotic. Yes?
Could it be equivalent, or can it be that you have one map that is chaotic and the other map is contained in some part of the first map, not topologically equivalent, but something regional?
Then you can probably reduce once. No, because you cannot reduce. With the notion of topologically transitive, it means precisely you cannot reduce your set. So no, you cannot. Either they are precisely topologically equivalent or you have nothing. So no, you cannot decompose further. This is a notion of topologically transitive. Any question or remark? So we have a definition of what is chaotic iterated maps, two conditions, and it implies sensitivity to initial condition. And now we proved, we have an example where we prove, or we have even two examples, but they are topologically equivalent, where we prove that it is indeed chaotic. And now I want to go to the last section, which is about Cantor spaces and strange attractors. So this is probably 7.7 Cantor spaces. Plus strange attractor. Okay. So I will use again this tent map and I will recall. So we consider still the tent map, but not only for the parameter 2, we consider T mu from R to R. And I will consider mu strictly bigger than 0. And I recall what is this. It is mu over 2, 1 minus absolute value 2x. This is a definition of the tent map, which is rather simple, but you have an absolute value. So often you need to consider two cases. And for mu is equal to 2, we could divide into two cases according to the absolute value. All right. So the first observation is that if x is not in 0, 1, and we will use this observation many times, then T mu of x, when you apply it m times, when you iterate, this is going to minus infinity. If somebody wants to, you can just check, or you can do some numerics, check. If you iterate T mu, so you start with the x outside of 0, 1, you iterate, it's just going to minus infinity when m goes to infinity. So this is the first observation. So it means if we don't want to go to infinity, we have to look at what is inside 0, 1. Going to minus infinity is a boring case. So we want to avoid this. So now the second observation. I'm going to define a first set, which I call lambda 1, which is 0, 1 over mu union 1 minus 1 over mu 1. So it's a union of two parts inside 0, 1. So we have a first region and a second region like this. And the second claim is that Tm mu of 0, 1 minus this set is also going to minus 50. Okay. There is no contradiction. First, I observe what was outside. Then I observe what is the complement of this set, and I'm claiming it's also going to minus infinity. And I continue. The third observation, I'm going to iterate this process. So now I define lambda 2, which is going to be a subset of this one. Yeah, in fact, you can put either 0, 1, or R. We already studied what is outside of 0, 1, so I can concentrate on what is inside, but I could replace this by R, it's the same. So now I define a new subset of this one, which is 0, 1 over mu square union. I have written this in the notes, so you don't have to copy everything, but it's a union of 4 subintervals. Yes. Oh, yes, you're right. Thank you. Okay. Yeah, it's a bit boring. I will not write so many, but 1 over mu, thank you. Union. Now, I will not write more than just a second. 1 minus 1 over mu. 1 minus 1 over mu plus 1 over mu square, and the number 4. 1 minus 1 over mu square 1. So what I've done I have subdivided this, so I'm taking, this is lambda 2, probably. Oh, yeah, probably. And you observe these intervals are of length 1 over mu square, because this is of length 1 over mu square, this is of length 1 over mu square, this is of length 1 over mu square, this one is also of length 1 over mu square. And the second or the third observation is T mu, again, m of 0, 1 minus this lambda 2 is also going to minus infinity when m goes to infinity. And now,
If x is equal to 1/2 and mu is equal to 2, it doesn't.
but look, oh, sorry, I made a mistake. Sorry, thank you. Sorry.
Oh,
Sorry. In the note, it's correct, but yeah, I made a mistake. Sorry.
So like x is equal to 0, 1, don't you get 0 or?
Yes. Yeah, 1 is sent to 0 and 0 is stable.
Well, then if you put that to infinity, or you get minus infinity.
Oh, thank you. So I'm doing some mistakes. If m is not in 0, 1. Okay, thank you. If not I started by, sorry, I did this. So I start by saying that what is outside is going to infinity, minus infinity. Then I'm saying now I look at what is inside. If I'm not in the right region, you apply it once, you already go outside, and then you go to infinity, minus infinity. Then I'm saying if you are not in the red region, it's the same. You go to minus infinity. Sorry, so it was x is not in 0, 1. That's why then I restricted to.
That doesn't work either. No?
I hope it works.
When you're in 0, 1, 1 minus.
There is no contradiction. I'm not claiming anything for 0, 1. I'm not claiming.
Here.
Check.
Which one are you taking?
0, 1 minus, so outside of this set.
Right, but that's still including 0, 1.
Yes.
So
there is no contradiction. The first statement is value. Which one?
I think it's positive, right?
Which one?
0, 1. Well,
okay, please check. I hope there is no mistake. It's difficult to do it in real time. And I believe it should be correct.
Well, if I take like 1/2.
But 1/2, it should go to infinity, to minus infinity.
Yeah, but 1/2 here is u over 2. Positive.
no, there's a 0 after 3.
Okay. Let me continue. Maybe there is a mistake I need to check, but I cannot do it. I hope there is. Now you scare me. Suppose it's correct. Doing some computation in real time on the blackboard is something horrible, because for sure you get nervous, you do more mistake than anything. So if there is really a mistake, I will correct it, but probably the ID is correct. Maybe I've done a mistake. So I subdivide the first set into a smaller subdivision, and I'm saying that if you're not in this part, it goes to minus infinity when m goes to infinity. And then recursively, we set lambda m as, so I don't want to write all things, so there is an iterated or a formula which says you take the set and you multiply, so be careful, it's a multiplication. You take a set and you multiply it by 1 over mu. So each entries, you multiply them by 1 over mu, and take the union with 1 minus 1 over mu, this same set. So it's really the same process as I did from here to here. I took this set made of two subsets. I multiplied by 1 over mu, and that's why I get, or I got these two from the first part. And the second part is I took 1 minus 1 over mu times this, and I got these two sets here. So you can do it iteratively. And the statement then T, oh, I should take a different letter, Tn of this lambda of 0, 1 minus lambda m is going to minus infinity when n goes to infinity. You need to work a little bit, but it's an iterative process, so you can do a proof by induction. Okay, so it means only some very small part are not, oh, so far I have not given the answer for all of them. So what I do finally, I'm going to define lambda, which is the intersection over m belonging to n of lambda m. Probably I need to put for once a star because it contains 0. So this set is quite strange in the sense that you take the intersection and you can observe it does not contain, so lambda, because lambda does not contain any interval. This is the first observation, and you can rather easily see it for the following reason. As I said, in the first step, this interval was of size 1 over mu. The second step, these small intervals are of size 1 over mu squared. So here, for this set lambda m, all subintervals are of length 1 over mu power m. And mu is bigger than 2. So it means this is becoming smaller and smaller. And now you take the intersection, so you have intervals which are smaller and smaller and smaller. And at the end, they have no length. No.
In the exercise, you use t power, like you use t power m. Is it t applied n time, or is it t to the power m?
No, it's an iterate map. So you iterate. No, this notation, please. I told you several times, t power 2, you should think about it as t2 of x is t of x. It's iteration.
Sinus.
Sorry?
The sinus.
Okay. Okay, this sine square was, of course.
Big bracket around the.
Okay.
Anyway.
I had not thought about it. Good. Good. We learned something. Notations are very, very important. This I should write it as T. I already mentioned. This would be the one notation. It's a composition too, but it's a bit heavy. All right. So what we observe, these set lambda m are composed of subintervals of size 1 over mu m, which goes to 0. And it means, if you just think for a while, the intersection contains no interval. Otherwise, you would have a contradiction. If you take any interval, you say it has a size epsilon, then by taking m large enough, it's not in this set because all subintervals are of a shorter lengths. And the second observation where you need to think a bit about it, it's lambda is of Lebesgue. First here, don't worry about this, of Lebesgue measure 0. What is the Lebesgue measure? The Lebesgue measure is the way you precisely mathematically measure this length. And I'm just saying that if you try to measure this set, the size of this set is 0 for the usual way to measure it. I cannot tell you exactly. It would take 2 or 3 lectures to speak about this. All right. So just saying it has, the problem is, so now you can wonder, oh, but is there any point? Is it, question, is this the empty set? The answer is no. The answer, it's not the empty set, and you can check it because you can still find some points. What points you can find? This set lambda is not empty since it contains. So now the notation is again quite ambiguous. It contains T mu m of -1 of 0 or 1. What does it mean? This is the inverse map. And I'm not claiming that this function is bijective, but what it is, take 1. Let's take first 1. It means you look at the point which are sent to 0 and 1. It's a pre-image, right? So you look at the point which are sent by t on 0, 1. And then you do the same. You look at the point which are sent after 2 iterations on 0, 1. And you do the same for m iterations. And it turns out that these points belong to this set for any m. For any. So it means you can find plenty of points. It's not intervals, but you can find plenty of points which still belong to this set. In fact, it's inclusion. It's a subset included in this. So yeah, it's not empty, but the problem is it's an uncountable set. You remember for Lebesgue measure, if you have a countable set of points which are measure 0, you know it's measure 0. But here it's uncountable, so you cannot use this argument. So you have to be a bit more careful. But it's possible. Why it's possible? Because mu is bigger than 2. If you look at, I said these subintervals are of this size, how many of them you have, and then you do the ratio. So you count the total length. So it means you multiply this by 2 power m. This is a number of subintervals. But still, when m goes to infinity, this product goes to 0. This is how you show that it has the Lebesgue measure 0. All right. So we have a set made of points, many points, which satisfy the following thing. By construction, we have 2 things. If we apply T mu on any point of this set, we are still on this set. So it means this set is invariant. And if X is not in this set, then if you apply Tm, if you apply T enough times, it goes to -infinity when m goes to infinity. So it means in my interval, let me make it bigger. Let me copy this. We have this interval 0, 1. I found some points. I cannot describe them, but we have defined some points which are stable. This is the set lambda. These points are stable under applying t. And any point which is outside if you're not in this set and you apply t enough time, will go to minus infinity. So this is what we have constructed. So think about it. It's not trivial, but it's possible to do. Any question? Yes, I'm going to mention it. Yes, I haven't introduced this word now, but yes, I will do it in a few minutes. Okay. So now this set has two properties. One is rather, I already mentioned, so properties of this set. This set is totally, we call it disconnected, which means no interval inside. So no matter small, it doesn't contain any interval. So this is something I mentioned. But there is a second property which is more difficult to fully understand. It's this lambda is perfect. So what does it mean? And I put a link to Wikipedia. It means any point of lambda is a limit of a sequence of points in lambda. So what does it mean? This is very difficult to completely understand. I'm not sure I even understand it. You probably know, let me take an example just for trying to explain this notion. You take the sequence 1 over n, any integer. You know this sequence, you have 0, you have 1, 1/2, 1/3, 1/4, and you can continue. It converge to 0. Nobody is surprised if you take these 1 over integers, you are approaching 0. So 0 is a limit point of this sequence. It's not a point of the sequence because 0 is not a 1 over something. It's not 1 over an integer. So it's not a point in this sequence, but you approach it. It turns out that this lambda, if you look carefully, all points are themselves limit of a sequence of points which belong to this set. So it means these points are becoming closer and closer, but each of them is a limit of the sequence. I told you it's really difficult to understand it fully, but think about this example. But it means if it would be this, it means 0 would be a point, but it means 1, we would have also a sequence converging to 1 if it is in this set. 1/2, we also would have a sequence of points converging to 1/2. And each point of this sequence, we would have a new sequence converging to it. So this is a notion of perfect. There is a link to Wikipedia. I don't know if they give some examples, but again, you can check very carefully that this is true on this example, but it's not easy.
I can't take the sequence of a constant sequence of this point.
But all points.
Yeah.
Ah, you mean. Okay.
The same being closed.
It implies that it is closed. It implies that it is closed because it contains all limit points, but it's not equivalent at all. So it implies that it is closed. But no, it's very, very special. You know, a closed interval is closed, but it is not at all. Okay. So it turned out that any set having these two properties has a name. So any set, so sorry, I should say in Rn, any bounded, I add closed because we haven't proved that it is closed, but I think it's by definition. So I just added any bounded closed, totally disconnected. Imperfect set is called, this is just a name, a Cantor space. This is just a definition. So again, it's not, this one is easy to understand. This one is much more complicated. But there is a famous example which was constructed a long time ago, the Cantor set, and you can find plenty of information on internet. But the Cantor set, which is obtained by dividing an interval into 3 parts and removing one, and you iterate this, is a Cantor space. In fact, it was the first Cantor space which was exhibited. So the Cantor set is, or has these two properties, but the one we have just constructed, so the lambda we have constructed, is also a Cantor space. Lambda obtained by the 10th map T mu is also for mu bigger than 2. For mu bigger than 2 is also a Cantor space. This is why I introduced this notion. Okay, so if you have never seen what is the Cantor set, because this is unique, just look at the construction. I gave a picture in the notes, but it's again, you remove 1/3 of each subinterval and you do it iteratively. And here, in a sense, we do the same thing, but the construction is a bit more complicated because it depends on a parameter mu. So we have a family of Cantor set. Any question? So now, as one suggested, this Cantor set lambda is not attractive. It's exactly the opposite. Remember, I said we have this set, which I cannot represent. We have this set lambda. And I said if you are outside, you apply Tm, then you would go to -infinity if you apply Tm many times. So it's exactly the opposite of attracting. It repels everything. So I need to define the notion of repeller. So I will recall the notion of attracting set or attractor, and the opposite is a repeller. So I just recall that a set or an invariant set, an invariant set. So invariant set means that when you apply f to lambda, you are still at lambda. This is a notion of an invariant set. An invariant set is attracting if there exists a U open, I already gave this definition, containing lambda and such that the distance between fm of x and lambda it's an iteration of f. This distance goes to 0 when m goes to infinity. This is attracting. It means any or for any x in U. So it means you approach this set lambda. This is a notion of attracting. Now, a kind of opposite. Lambda, the invariant set, is repelling. So it's not attracting, it's repelling if there exists U open containing lambda such that what you want to say you are going away from it. It's a bit less precise, and I don't fully understand why it's a bit less precise, but you would like to say the distance is increasing, but it's not exactly this. So if there exists an open set containing lambda such that for any x in U minus lambda, so not in lambda, but in U, there exists a certain m which can depend on x. It's an integer such that the fm of x is intersection with, or is not in U for m bigger than x. Okay, so what does it mean? You have your, let me do a simple, oh no, 2 dimensions, it's easier. This is my set lambda. It's repelling if there exists a U, so that any point here, when you iterate, it would go outside. It doesn't mean it would immediately go outside, but after a while, so up for m bigger than mx, it would leave you. This is a repelling set, right? And we know already that if we are very close, probably it takes longer to go outside. That's why this m can depend on x. You don't expect that you would go very fast if you are very close, because your speed at the beginning would be almost 0. This is a notion of repelling. You go away, but at a speed which depends on where you are. And it turns out that the set lambda obtained before is repelling and a closed set which is repelling is called a repeller. Repelling is called. So it's exactly the opposite of attractor. If it is an attractor, I already defined it's attracting. If it is a repeller, it's a E, but apparently you can also write it with a O. Both are accepted. It's exactly the opposite. Everybody around it goes away from it. So we have these 2 situations we have seen before. Some attractors. Now the set lambda I have constructed with a tent map is a repeller. Okay. Yeah. I guess so. In the definition, it's And you cannot, if everything is in a box, it cannot go very far away. Of course, in my example, it was going to minus infinity, but suppose for some reason I put it in a box, then it cannot go very far away. No, these for distance. I'm in a metric space, so you can think about the Euclidean distance if you are in Rn. This distance. All right. So what we have seen, let's try to summarize. We have seen the notion of attracting an attractor, repelling and repeller, and I define what is a Cantor space, and the Cantor set is one example. And now the next definition, and the definition contains something which has no definition, unfortunately. So I'm going to define what is a strange attractor. So an attractor or a repeller is strange. It's strange. It's lambda. It's strange if the underlying so we are always in this system of discrete time dynamical system. So if the underlying discrete time that I shouldn't, okay. The system is chaotic, and we have defined what is chaotic, and lambda is fractal, which I haven't defined. So I need to say more about this. Yeah, the definition is not so good because this notion of repelling or attracting are always defining according to a dynamical system. So you have a dynamical system and you say what is an attractor or a repeller. Just a set itself, it's not attracting or repelling, it's just a set. So you need a dynamical system. So what is this notion is an attractor in the framework of a dynamical system is strange if when you consider this, which is F restricted to this set is chaotic, and chaotic, remember, it means two things. It means topologically transitive, so you cannot decompose it further, and it means dense periodic points. And it implies sensitivity to initial condition. So if it is chaotic, and it's a fractal. So now, what is this? And if you look on Wikipedia for fractal, you will see there is no definition. There is no definition, so I cannot really define it. But there is one property which everybody agree as a definition. It has a non-integer dimension. It helps you a lot, I'm sure. It has a non-integer dimension. So I have to define what means this. So what does it mean? It's difficult to give a definition of this. There are plenty of framework where people construct fractals according to some rules. So it's not a unique definition. But what a property that all fractals have is that you can define a notion of dimension which is not an integer. So I will define one of these dimensions, which is the most famous one. And whenever you have an object which has a dimension which is not integer in this framework, you can call it a fractal. So again, it's usually defined in terms of a certain iterative construction. There is no unique definition, but it has a property which is shared, is that it has a dimension which is not integer. So I want to focus on this simply because I cannot give you a definition. Probably you can find a definition in a restricted setting, but somebody will say, no, 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 no. I am able to construct this, and it doesn't fit in your setting. I also call it fractal. So probably depending on what you're interested in, you can find a definition, a local definition, but it's not a universal definition. Think about this like this. All right, so I want to define this non-integer dimension, and more precisely, I will define the Hausdorff dimension. And this is the last thing. And we will see that the object we have introduced have a Hausdorff dimension, which is well defined. So a fractal, which I haven't defined, has a non-integer Hausdorff dimension. I'm not even sure that it's enough in the sense that there are other dimensions, but this Hausdorff one is probably the main one. So I will define this Hausdorff dimension. Okay. If you have any question, you can always ask me. So let's look at what is this Hausdorff dimension. So for this, I will just recall something. If I consider a set, what is a cover? A cover is take some subset and cover it. This is not so difficult. You cover it completely. This is called a cover of my initial set. Right. This is a cover of this initial set. I'm covering by balls, for example. So I will use this word in a first. So first of all, for any set U inside Rn, this construction is in Rn. We define first what is the diameter of U by du. It is the sup over all x and y inside U of the distance x minus 1. And you can check, it means for this set, the diameter is going to be the longest distance inside. So this is a diameter sup of x minus y for all xy in U. This is a diameter. Okay. Now, this is a cover. I just recall, this is a notion of cover. And I will assume that cover are countable. Cover by a countable number. For example, why I need countable means at most it is you have n elements, a cardinality of n. So you can say this is the first one, the second one, the third one, up to infinity. So Q is also countable, but R is not countable. And for example, the entire line can be covered by small balls. A countable number of small balls, take a ball of size epsilon and cover the entire line. This is still a countable covering of R. So countable doesn't mean it's not a big limitation that you find a countable covering. Okay. So now, it's a definition in a few steps. For any, so I consider set lambda. Consider lambda, any set lambda in Rn. I consider alpha a positive or zero real number, and delta a strictly positive in number. So we set, I'm going to set H alpha delta of lambda. So I introduce an object. So I will explain. It's not trivial, but I think it's interesting. Lambda. Okay, this is the first definition. What does it mean? I take a set lambda. The red one is a set lambda. This is lambda. I take any cover. But any cover, here I draw balls, but I'm a bit more general. I'm drawing a cover with sets which have a diameter at most delta. So it's not necessarily balls. They can be of this type, but this length is at most delta. Think about balls, but it can be square. Sometimes it's useful to consider square or other things. So I consider any covering of the set lambda with objects of diameter smaller than delta. And what I do, I take their diameter, I sum them, but with a power alpha. So I take the diameter, I put power alpha, and I sum this. Right? It can be infinity. This sum can be infinity. So this number, be careful, it is inside 0 infinity. There is no problem. I accept that it's infinity. So I take a cover with balls. I'm going to say balls, but it's more general. But let's say with balls of diameter at most delta. I cover my object. I then take the sum of these diameter power alpha, and I take the infimum. This infimum is over all covering. So I take all possible covering of this set. But fortunately, these things are not so complicated, because what happens when delta decrease? Observe that this H alpha delta of lambda is increasing as delta decrease. It might seem strange, but no, it's quite clear. If you decrease if you decrease delta, you have less covering. You have less available covering because the one with big balls are no more available. So your infimum over all coverings is on a smaller set. So if you take the infimum, you have less choices, so of course it increases. So when delta decrease, you have less covering, so the infimum automatically increase. Right? So it means, as I said, since less covering are available, you have less choices. More time is flying so fast. Okay. So this is the first observation. So it means I can set H alpha without the delta as the limit when delta goes to 0 of this H alpha delta of lambda, because it's increasing. So again, it can be infinity. And this is, if you think about it, it's the same as the supremum over delta bigger than 0 of H alpha delta lambda. And again, it's belonging to 0. I'm not claiming that it's finite. But it's a way to first eliminate this dependence on delta. And a nice observation which we want to have, of course, is if, which order I took, if U is inside V, then H alpha of U is smaller than H alpha of V. This is not so difficult to observe because you need to cover less. So you have or equal. So this is a nice property which you expect. If you, my aim is to define something of a measure. A measure of this set should respect this. It should increase with the size of the object. Okay. If you have any question, you can always interrupt me. Now I want to, alpha is not fixed. I will need to say something about this alpha. So my next aim, now I consider delta smaller than 1. This is not a big restriction because look, I'm looking at the limit. So I can always assume this. And we consider, therefore d of uj smaller than delta in the construction. Then I want to compare d uj power beta with d uj power alpha for beta bigger than alpha. Since this is smaller than 1, when I take bigger power, it's becoming smaller. So we're having this direction. Okay, because it's smaller than 1, if you take power 3 instead of power 2, it's becoming smaller, right?
For this strict degree equality here.
Probably not, but probably not. If you don't like it, probably you can forget it. It's not harmful. It doesn't matter. Then the second observation is duj of beta. I can always write it as duj of beta minus alpha times duj alpha. I can always do this. There is no, I'm still in the case beta bigger than alpha. And I observe that this is smaller than delta beta minus alpha duj of alpha. Why? Because this guy is smaller than delta. And maybe you can even forget this. So you have this. So far, it's not so difficult. And from this, I can, since this is true for any uj, I get that from this, you get that the sum over j of d uj power beta is smaller or equal to delta beta minus alpha sum j d uj of alpha. You just do it for all set, right? And from this, because it was a infimum, let me write it. Hold on. I get, it's called delta beta. It's a bit long, but if you think about it, it's really not difficult, this part. Okay, so what I'm saying is that this guy, which depends on delta, is smaller than this. It follows from this inequality. And then since this one is smaller than this one, because this was a supremum, we get this. And here I don't have a delta anymore, from which I can say something. And this is probably, I'm going to define a function that you have never seen. Because look, this one is I wrote it, it's a supremum over all delta. So it means this one is always smaller than its supremum. It's really by what I have written before. So we get if H alpha of lambda is smaller than infinity, then we get that H beta of lambda, which is, remember, it's a limit when delta goes to 0 of H beta delta of this. You now replace by what we have what we have here is the limit delta goes to 0 of delta beta minus alpha of H alpha lambda. If it is smaller than infinity, automatically it is 0. Of course, it works only if I assume that the first guy is smaller than infinity, otherwise I cannot conclude. So I'm going to define now the Hausdorff dimension. Who has ever seen this construction? You had seen it, Haruki? No? Okay. So the last now, I should have mentioned I'm always in the case beta bigger than alpha. So whenever H alpha is smaller than infinity, one with beta bigger is 0. Then we set the Hausdorff dimension, which is denoted by dim with a H. It's for Hausdorff. The Hausdorff dimension of lambda is the infimum over all beta bigger or equal to 0, such that H beta of lambda is equal to 0. So it sounds a bit strange. Let me write one more line, and then I will represent something. This is also equal to sup of alpha bigger or equal to 0, such that H alpha of lambda is infinite. So the strangest function you have ever seen, what is the function H alpha of lambda as a function of alpha? If you look carefully, it's a function taking the value infinity, infinity. This is infinity. It takes the value infinity, and suddenly there is a jump, and it takes the value 0. So you need to think carefully. I'm not sure you can do it within 2 minutes, but this is a function H alpha as a function of alpha. And I call exactly this value, I call it dim H of lambda. And by the way, n is always here. So the Hausdorff dimension, if lambda is in Rn, and I started with this, it's always smaller than n. And it's possible that it is 0. It means this infinity can, in fact, be always 0. Okay, so this is a definition of this Hausdorff dimension. It's a value where this function H alpha jumps from infinity to 0. A few examples. What is the Hausdorff dimension of a point? Think about it. Yeah, you can certainly answer the Hausdorff dimension of just one point is clearly 0. And you can directly get the Hausdorff dimension of a finite set is also 0. Okay. Now, what is the Hausdorff dimension of the lambda, which we have seen? Lambda, the strange repeller. This is still a computation you can do, the strange repeller of T mu. It turns out that this is log or ln of 2 over ln of mu. This is something you can check by hand. What is the Hausdorff dimension of the Cantor set, the initial Cantor set? It is ln of 2 over ln of 3. I gave one more example. Oh, by the way, here you might complain. Very good. Why these two dimensions are not the same, while we have seen that both these two are Cantor space. But remember, Cantor space are defined with notion of topology. You can deform. Here we are measuring. And measure is something which is not constant through topology. It's not something, a measure, when you deform something, clearly the measure, the volume or anything can change. So there is no contradiction. Topological information are conserved through topological equivalence, but measure, no. So there is no contradiction, but it's a very good observation. So the Hausdorff dimension of this repeller depend exactly on the mu, even though all of them are Cantor spaces. Yes. And the last thing I can say is, you remember we look at the Lorentz attractor a long time ago when we were discussing continuous dynamical system. So and I said that the Lorentz TZ or Z now, I'm no more sure. I think, okay. But the Lorentz, just look at section 6.2. The Lorentz attractor has a Hausdorff dimension of course, this one, we can only get it numerically because we don't have a very specific formula for it. But it means we can also define for this by covering with small boxes, and you do this construction. It's not only for iterated map. It's just a set which is invariant, and we do this construction. So it means it is a fractal with a definition of a fractal has a Hausdorff dimension, which is not an integer. Okay. So this is the last thing I wanted to say today, but no, there is still a movie. So I need, can you turn on the projector? But first, is there any question? Yes?
Definition consistent with some common belief, like 2D plane.
Yes. If you take an object in 2D and you compute the Hausdorff dimension, you will get 2. I mean, a ball, a sphere do the exercise. Oh, no. Of course, this is consistent with covering. And that's why in the picture, the n is the biggest one. So you cannot, in a space of dimension 3, you cannot have anything of dimension bigger than 3. And if you take a ball, it's of dimension 3. Oh. And a plane would be of dimension 0. So there is no contradiction. In R3, a plane is of dimension 0. Dimension. Hausdorff dimension, I think it's also 0. Oh, no, I'm not. No, I think so.
I mean, the measure should be 0.
Okay, exercise for somebody. What is the Hausdorff dimension of a plane in R3? I'm pretty sure it's 0. But
Like Hausdorff measure.
No, Hausdorff measure maybe. Okay, so exercise. What is a Hausdorff measure of a plane in R3? I don't know the answer. So
in R2 it's 2, but in R
it
might not be 2.
Okay. So I'm going to share. I will stop sharing the camera and I will share my screen in a second. So just wait on, and I need to. Okay, wait a second. I first deal with this. So I haven't done this before, so wait a second. Um, Harumi or Itisham, can you see the slides? You see the slides? And online, here you should also see the slide if I connect.
Yes, I can see this.
Okay, good. Thank you. So now I need okay. Thank you. I will make it bigger. Oh. I don't know if I have a... Do I have a way to eliminate this line? No. Okay, I will deal with this. So, as I said, it's a presentation, or it is written, it's a presentation prepared by one of my students, former student. Yes. Why? Okay. It's a Lorentz 1963 model, which is the Lorentz attractor I have defined before. And the aim was to play with a strange attractor. So I will explain. So you will see. So this is the equation we have seen. We have seen this three-dimensional differential system, and we had three constant, and here they are fixed. And if you take an initial condition and let this system run, you get the first picture. And if you keep track of all trajectories, you get this attractor, which we have seen in the notes somewhere. And now we want to study when we go from one side to another side of, some people call it the butterfly. Here it's called warm or cold regime. But you can see clearly there is two sides, and the aim is to stay on one side. Unfortunately, it's a chaotic system, so it's very difficult to predict when it's going to change from one side to the other one. And the picture, the big picture here, is precisely the measure of the x coordinate. So whenever you are above 0, it means you're on one side. When you are below 0, it means you're on the other side. And as you can see, sometimes you stay a few times on one side and then move to the other side and come back and forth. If you have any question, you can ask me. But this is a representation of where we are. Are we on the left wing or on the right wing? And it turned out that, okay, we did some simulations. Every 2.3 cycles, so a cycle is going from, you can easily guess the definition of a cycle. It's from a maximum of x or to a minimum of x, the x variable. So on average, we change the side of this butterfly every 2.3 cycle. But it's very difficult to predict when we are going to change. And again, my aim is to stay on one side. So how can we do it if it's very difficult to predict when the system changes from one side or to the other one? So there is a technique. Okay, so this is the aim. As I said, instead of going alternatively on one side or on to the other one, we want to do something on the system, perturb a little bit the system in order to stay on one side, but we want to perturb it as few, not so often, and not put too much energy in the system, because the final aim is to do this for other systems, so we want to minimize our action on the system. But the aim is to stay on one side. And in order to make the thing more complicated, it means the observation contains some noise, so we don't know exactly where is the system. It's always with some randomness in the position. So we never know the true value. of the state, so we don't know exactly the coordinate where we are, of course. And what is the idea for doing this? We anticipate. So we suppose we measure the system at a certain point with some error. Then we forecast its evolution because it's a dynamical system. We can forecast its evolution. And we see if after a certain period of time, it's still in the same region or if it goes in the other region. So if it stays in the same region, we let the system evolve for a certain time. If we predict that it's going to change in the other region later, we do a small perturbation. So this is what is represented. The first forecast, we forecast it's the first green light. We see that, it's a picture, we anticipate that it's going to stay on the same side, so we don't do anything. And we let the system evolve up to this t plus 008. Then at t plus 008, we again we measure with some approximation, and we observe that it will go to the other side in the future after a certain time. So we are going to perturb a little bit, and this is what is represented. The second time we do a small perturbation. But we need to decide what is a good perturbation, because if we go in the wrong direction, we would maybe go even faster to the other side. So we have to decide what is a good perturbation. And this is the technique. So at the very beginning of the line, this is where we measure the approximately our system. Then we do 3 evolutions. So we take 3 initial points which are very close, and we let it evolve. And these are the light blue trajectories. And the idea is it stays for 2 of them on the first line. No, for 1 of them in the first line, it stays on the same side when we predict. For 2 of them, it goes to the other side. This is why it goes below the 0 line after a while. So we want to say, oh, this is dangerous because our real system might go to the other side. So we are going to do a small perturbation, and we are going to perturb it in the direction of the blue system, which does not go on the other direction. So now we have a direction. The direction is given by the blue evolution, the top blue evolution. So among our 3 initial condition, we push a little bit in the direction of the one which is still on the upper side. And because it's an experiment, we compare. So then we do the evolution. The red evolution is the one after our small perturbation. And indeed, it's good. It stays on the correct side. And we see, oh, it was necessary to do it because we also do the evolution with a true evolution, which is the black one. And indeed, the true evolution shows that it would have gone to the other direction. So in this case, we were clever to put it back on the right track. So this is a control which has been successful. But there are other situations. There is also some false alarm. So here we suspected that it would go in the other direction. So we did an action, but it turns out that it would have been not necessary, because when we look again at the black evolution, which is a true evolution, it doesn't go. So it was a wrong alarm. So we did something, but it wouldn't have been necessary. And the third is we still do something, and unfortunately, it's still the true run, the truth is the black one is going in the other side, but even though we perform this small perturbation, at that time it would go in the red one. But still, we are doing to perform this iteratively, so at a later time, we can still correct our action. But it was an action which was not enough here. And indeed, on the left, you can see the true evolution. And on the right, whenever it's yellow, it means whenever it changes the color, it means we perturb a little bit. Either if it is yellow, it means it was a wrong alarm. When it is red or green, it has a different meaning. So for many times we could let it evolve. We are not scared, but suddenly we suspect that it would do it. But when it's yellow, it means we were too cautious. We did something when it was not completely necessary. But we were able to keep it on this side forever. So it means this method, even though it's chaotic system, if you do the correct push at the correct time, in the correct direction, you keep it on one side. But then there are different problems because we want to minimize our interaction. How long do you need to focus in advance in order to do this? So there are plenty of parameters that you can adjust. And here, this is just a representation of in which direction we perturb. So again, now it's going for a long time. We don't do anything. We don't forecast that it's going to move in the other side. And after a while, we suspect again it would. So first, it's a wrong alarm. You will see it's yellow. And suddenly it was red, so it was necessary because otherwise it would have gone on the other side. But we were able to correct on the next step. And in fact, we were able to keep it on one side. This is how to defeat chaos. And this is another representation of what happened. On the yellow part, this is where we put an action. And the difference in the first and the second line is the intensity of the action. As you can see, the first one, it's a weaker, the D, which measure how much we push, is smaller than in the second one, but we have to do it more often in order to keep control of it. The second one, we do it less often, but we have some dangerous situation at the end. Still, we were able to keep it on the correct side. So then you can fit some parameter, you can discuss many things. So it was part of a study of a student. And the idea in very far away is that how to control some more complicated. It's often called a toy model because you have control on everything. But there is already one which is more difficult, the Lorentz 96, because it's 40-dimensional. So you need to think about space 40, and then you can deal with other simulations. OK, so I wanted to finish this year with this presentation. Thank you. I wish you Happy New Year, Merry Christmas. And I have some chocolate and biscuit. Please help yourself. Please take enough. I'm sorry for those online, you cannot take them, but for those in this room, please help yourself.